section 3.3 is going to use a lot of the same ideas as section 3.2 did. What did we study in section 3.2? Do you remember? Maximum and minimum points. Yeah, we discovered maximum and minimum points. Relative ones, or local ones, and absolutes, right? We did both of those pieces. In particular, the relative extremas are the ones that are going to be helpful to what we're talking about today. Do you remember how we found those relative extrema? What did we do? Okay, so first we took a derivative, and then we set it equal to 0 to solve for, to find critical points, exactly. And we also looked at some of the spots. We didn't have a lot of them, but there are occasional ones in your book when you're doing your homework where they were spots where the derivative didn't exist as well. We didn't actually have any of those that created critical points for us, but that is a possibility as well. It doesn't have to be them equal to 0. It could be them equal to doesn't existing, basically, like denominators equaling 0 and so forth. All right, so this idea of having a derivative do something for us, a derivative telling us something about the original graph, is what we're going to be using in this section as well. So we're going to be talking about increasing and decreasing functions. The first thing I want to do is I want to actually define very specifically what it means for it to be an increasing or a decreasing function. This is kind of one of those things that if I asked you to look at a picture, you'd be able to just tell me why. I mean, you just say, yeah, it's doing this or it's doing that. But this is the formal description of what it means to be increasing or decreasing. So an increasing graph is a graph where when x1 is less than x2, y1 is less than y2, or f of x1 is less than f of x2. Visually, what that means is that if we take 2 points, x1 and x2, come on, and we looked at the points that exist, then the first one's y value would be smaller than the second one. And then somewhere in between, we have the graph doing this, or maybe it does this. Maybe it's just flat out straight. It doesn't really matter. But the idea being that the first location is lower than the second one, and this graph increases. And you guys knew that that's what it means to increase. You probably didn't think about it in terms of this sort of inequality. Decreasing is the same idea. So we still have to have the x value, x1 is less than x2, but now the f of x1 is greater than f of x2. So the picture for that one looks, again, much like the one we just did. x1 here, x2 here. But then instead, the x1 value is higher than the x2 value. And they're connected in some way between them, so that the graph decreases. So think with me then about derivatives here. First graph. This graph is increasing. What can you tell me about the derivative between x1 and x2? It's positive, right? And remember, derivatives really is just talking about slopes of tangent lines. If you look at this graph's increasing, its derivative is positive. What about the decreasing graph? Yeah, the derivative is negative, exactly. So when we're looking at graphs being increasing or decreasing, we could actually look at whether their derivatives are positive or negative. And that's exactly what the first theorem says. The first theorem says that if you have a derivative that's positive, okay, first of all, we've got a continuous function, but we have a derivative that's positive, then the graph's increasing. The original function is increasing. And if you have a derivative that's negative, then the original graph is decreasing. Now, you guys kind of know this because we talked about this back in chapter 3, or in chapter 2. Do you remember when we were talking in chapter 2 about slopes of the graphs and drawing slope graphs? In fact, you did it on your exam, right? You had to identify where the graphs were increasing and decreasing in order to talk about where the slopes were positive and negative to draw a slope graph or to draw a derivative graph. So it's not like this is a new idea, but we're going to be using it in a different way now. Okay, using that information in a slightly different way. All right, there's another theorem here. This is the first derivative test. It kind of combines what was on that last slide with the ideas of maximums and minimums from the last section. And that's the idea. So if you take a look here, the first one says that we have a derivative that's positive, which means the graph's increasing, right? And then it says we have a derivative that's negative, which is equivalent to saying the graph's decreasing. And it's decreasing and increasing along some intervals. So the intervals they give you, C is between A and B. So visually, need some more space here. Visually, we've got a number line, so to speak, where the A value's here, the B value's here, and C is somewhere in between. That's what that interval means. The first description that I circled in red, where it says the derivative is positive, that's happening between A and C. Okay, so it is increasing between A and C. It's going uphill. And then this part that I circled in blue says that it's negative, the derivative is negative, it's decreasing between C and B. So if the graph is increasing and then it's decreasing, what happens at C? It's a maximum, right? You can't go from increasing to decreasing if it's continuous, and it is. We were told that. You can't go from increasing to decreasing without having a location where you've got a relative maximum point, a local maximum point. It visually matches up with what we'd be thinking anyway. That's really good. So this point right here, C, would be a max. Now notice it doesn't actually say the derivative is 0, does it? So it could be a derivative doesn't exist, right? Because local maximums can also have that possibility. So it doesn't have to be a derivative of 0, but it does have to be a local maximum. All right, the second one says the same thing, but in reverse. This one, instead of it being a positive derivative to start with, it's a negative derivative. And so it's decreasing, right? And then instead of it being a negative derivative second, it's a positive derivative, so it's increasing. You've got the same interval that we just had, where we've got A here, B here, and C is somewhere in between. But the graph is now going to be decreasing between A and C and increasing between C and B. So what happens at C? It's a minimum, right? So this point right here is a minimum. Again, it doesn't mean that it's got a slope of 0. It may have a slope that doesn't exist, a derivative that doesn't exist. But it is a minimum value. And it's important that we know that the graph is continuous. Otherwise, it could, in theory, be a hole in the graph at that maximum or minimum spot, and we wouldn't have a max or min. So the fact that it's continuous is important for this to happen. Now, the last one, part C, is actually something that we talked about last time, but in a different way. This one says if you had the same signs on these two intervals, then the point is neither a maximum nor minimum. It doesn't say what it is. It's just saying it's not one of those things. We had an example. I gave you an example last time of a graph that looked like x cubed, and I gave it to you in another context. But if you were to take a look at this graph, x cubed, so this point is a maximum. What about at 0? This one goes from negative to negative. It's neither. There's nothing going on here. This is neither. And then how about from negative to positive? That's a minimum. So I have 3 critical points that I have to classify. I've got a local, let me use that blue again. I've got a local max at x equals to negative 2. I have a local min at x equals to positive 2. And I have at x equals 0. Why do I have neither at x equals 0? That's true, but what's going on in the graph? Do you know? What is it? Not quite.
Is it changing concavity, or is
It's an asymptote. Yeah, we may have a concavity issue there too, but yeah, there's an asymptote there. How do you know there's an asymptote there?
sounds fine in the original?
Because the denominator would be 0. So that's why there's an asymptote there. I guess it could have been a hole in the graph, but it isn't because the numerator didn't simplify with the denominator. That was part of what I erased, but yeah. So that's why it's neither, but that is a critical value. Any questions on that one? Okay. All right, we have one more. Directions are a little bit different on this one. This one tells us to find by hand all asymptotes and extrema and to sketch a graph. Now, I know that you've got calculators to verify this, so you should be able to make sure that what you get is actually the right answer, even if you don't have a back of the book on a problem, right? But you're going to show all the work by hand to see that you've got all the details here. So part of the by hand stuff here is finding the relative extrema. You have to find where you've got these peaks and these valleys. And this is one of those places where it's going to be really helpful for us to find the y value that goes with it, because we'll be able to plot an actual point instead of just showing the point along the x-axis. So we're going to find the relative extrema, and we're going to find asymptotes. You know how to find asymptotes as well. How do you find asymptotes? Right, you set the denominator equal to 0. And in this case, on this one, you'd end up having to factor for that. Okay, so we're going to do that. We'll do the asymptotes first, since that's the spot where we're kind of starting without any calculus involved. If I were to take this denominator and set it equal to 0, in fact, you know what, let me do it that way. We'll set our denominator equal to 0. So we've got x squared minus 4x plus 3 equals to 0. So what do I do on this one? I already told you just a minute ago. What do I have to do next? Factor. Or at least I would attempt to. This one does factor. How does it factor? Right, x minus 1, x minus 3, which means my x equals 0 where? At 1 and 3. So these are my asymptotes. Does that make sense? Okay, so that's finding the asymptotes. I've done that part. Next one's the relative extrema. So how do I find extrema? Derivative. That's a little bit more complicated than setting that denominator equal to 0, because this is a quotient rule that we have to do. You bet. All right, so we've got our derivative. How do I do my derivative for a quotient rule? Okay, so there's my denominator. What's the derivative of my numerator? 2x, good. Minus what? The numerator, x squared, times what? Yeah, derivative of the denominator. What's the derivative of the denominator? 2x. Thank you, Jamie. You bet. And this is all over the denominator squared, right? So I need to simplify that numerator, because that numerator is going to find where where I've got critical values that are not asymptotes. Is what it's really going to do for me. So let's find where how that numerator simplifies. Let's see. I've got 2x cubed minus 8x squared plus 6x minus 2x cubed plus 4x squared. Okay, so what simplifies in the numerator? 2x cubed, they just even go away. What else? Okay, so this is negative 8x and positive 4x, both of them squared. So what do I have? Negative 4x squared, and then plus 6x. Good cleanup of that. All right, now what? We're going to set the numerator equal to 0, right? Okay, so we want to set this whole thing equal to 0, or to be doesn't exist. We don't actually have to do the doesn't exist one, because that's where the denominator is already going to be 0, and we already did that once. I mean, nothing new came about. The denominator didn't change. I mean, we squared it, but it didn't change the factors. So I really just need to know where that numerator now equals to 0. So the numerator equals to 0. So I've got negative 4x squared plus 6x equal to 0. And yeah, factoring out an x would be helpful. Anything else I could factor out? A 2 might be helpful. You could factor out a negative if you wanted to. We won't, but then that would leave me with, what, 2x? Negative 2x plus 3. So I've got 2x equal to 0, so x is 0. And negative 2x plus 3 equal to 0. So what does x equal for that one? Positive 3 halves, actually, on that one. Yeah. So I actually have 1, 2, 3, 4 critical values, don't I? I actually need to have 4 critical values then on a number line to talk about relative extrema. I do have space, good. All right, so here's my here's my number line. What was my smallest one? 0 it was. And then what? 1. And then 3 halves, and then 3. All right, so this one's going to be a little bit less beautiful to pick numbers because some of them are tightly together, tight together. So some value before 0. -1. Between 0 and 1. 1 half. You can write in 0.5. We're going to do it on our calculator so that we don't have to worry too much about it. What about between 1 and 3 halves? 1.25. Decimals are good. How about between 3 halves and 3? 2. And between, or after 3? 4. So we're going to test all of these values into the derivative. I think, did we call our derivative g? Y. All right, so we'll use y of -1, y of 0.5, y of 1.25, y of 2, and y of 4.
Is that one prime?
What's that?
Is that one prime or y?
Primes, thank you. I left that out, didn't I? Absolutely, get those derivative notations in it, thanks. All right, so grab your calculator. I'm going to remind you, we did this way back at the very beginning of the semester. Remind you how you can do this really easily, okay? So you should hit y equals. You're going to put the derivative equation that we got into y equals. So in y equals, you're going to put, I would put the simplified equation that we've got down here. This one. All right, so put this into y equals. Make sure if your calculator is not set up to do something differently for you that you do the whole numerator in parentheses, if it's not in math text or not math type, and then the whole denominator in the parentheses is squared. After you put it into y equals, you can go into a table. Okay, does everybody remember how to do that? Putting that in y equals and then going into your table, into your calculator's table. And then once you're in the table, as long as your calculator is set up to allow you to input answers or values into your table, and it should be because we've done that before, you can actually put in these 5 values that we want. -1, 0.5, 1.25, 2, and 4. And again, what we're really caring about is it positive or negative? Right?
Yeah.
All right, so what happens at -1? Is it negative? Okay. How about at 0.5? At 1.25? Positive? At 2? And at 4? Okay. Oh, and there was one other thing that we didn't do on the last page, or last slide. We'll do it in a minute. So if it's negative, positive, positive, negative. Sorry, I hit a button funny. Positive, negative, and then negative. Then what's happening over here at 0? This is a minimum. At 1, we have neither, right? And that's because it was an asymptote. How about at 3 halves? That's a maximum. And at 3, that's neither as well. So these ones right here in red are neither. And they're neither because they're asymptotes. All right, so let's start putting some pieces of the graph together. We have one more thing that we were supposed to have found over here. It actually told us to find all asymptotes, and so far we actually only found the vertical ones. Sorry about that. Just sort of glossed right over that piece. We do need the horizontal asymptote if there is one. And this one does have a horizontal asymptote. Again, it's been a while since we've talked about this, but do you remember how we find a horizontal asymptote of a function like this? Yeah, the highest power. So the highest powers on top and bottom actually match on this one, right? Take the coefficients of it. Very good. So the coefficients on this one would be 1 and 1. So we actually have a y equals 1 asymptote. All right, so on a graph, some features. Well, we know that we have a asymptote over here at 3. And, I'm going to do this. That wasn't what I wanted to do. Take a look at that. Yeah, 3 and 1. So here's the one at 1. Remember, you draw asymptotes dotted. And then we have one at 3. And we know that my y equals 1 is also an asymptote, so it looks like this. All good so far? Now I know at x equals to 0, which is my asymptote or my axis here, I'm supposed to have a minimum value. I don't know yet what the y value is, but I can certainly find it. So if I go back to over here, I can find the y value that corresponds to an x value of 0. What is it? It's 0. If I plug in 0 into that original equation, I get 0 over something that's not 0. So that's a 0 value. So this 0 right here is 0, 0, and it's a max. I'm sorry, min, excuse me. So I've got a location on my graph, which is the origin, and that's the lowest point. It's the lowest point, relatively speaking. It's the lowest nearby point. We'll fill in some more detail about that in a minute. Let's see, what else do we have? 3 halves, thank you. So if we go back to our graph, we would want to put in, or to our equation, we would want to put in 3 halves. 3 halves is a little harder to put in, and you might want to do it in your calculator. So this is not the same thing as currently in your calculator, so I'd amend it. You want the original equation, x squared over the x squared minus 4x plus 3. And you want to plug in the number 3 over 2, or 1.5. Somebody get a value? I don't even think I wrote it down when I was doing it. Negative 1/3. Okay. So it's negative 0.3 repeating. It's negative 1/3. Okay, so over here at 3 halves, we have a little mark here as 1. So this is about right here. Does that look reasonable? That's 1.5. X equals 1.5, y equals negative 1/3. All right, now a few features here. That first one is supposed to be a minimum. This is the piece that's the most difficult to do. Normally, I would be tempted, if given this information without the max and min part, to draw this curve coming down towards this line x equal to 1, and then going to draw it up here. That's what I would be tempted to do. That's typically how these graphs look. But this one doesn't. It says this one should be a minimum value, doesn't it? So it actually has to come up from here. And yes, I know it crossed the asymptote, and I know that sort of looks and feels weird, but what you have to remember about asymptotes is that asymptotes are actually end behavior information. They're values where you get close to those asymptotes on the ends of the graph. You actually can cross them in the middle of the graph, and it's okay. Right? And then I'm supposed to get close. I am supposed to get close to this line, though, on the end of the graph, so it is going to have to come back up towards that asymptote. So it's going to look something like that. And again, you know you can check this in your calculator when we're done to make sure that it actually matches. This point right here at 3 halves 1/3 is supposed to be a maximum. So it's kind of going to look like a trapped parabola, except it's going to look slanted a little bit because it actually has to be the biggest value and it's not halfway between. So that's sort of odd, a little awkward. We don't actually have any information over here about maximums and minimums. That's okay. We do still know what happens over here, though. What does it say my graph's supposed to be doing up there in blue? Going what? Doing what? At 4? It's supposed to be decreasing, right? Over here it tells me that my graph's supposed to be decreasing. Well, that means my graph either needs to be looking like this because of the asymptotes, or like this. But only one of those that I just sort of motioned to the screen actually was decreasing, wasn't it? So it has to look like this. Because if I drew it underneath, it would be an increasing graph. Now you guys already have this in your y equals. Let's check it. Hit graph. If you don't have it in a standard window, you can do zoom 6 or zoom standard. Is it more or less right? Does it look pretty close? Yeah. That's kind of cool, right? All those details that we got from that piece of information. And your calculator can check it for you. I find that to be a very helpful thing because what that means is that when you get to a test, if I ask this question, you don't have to have a back of the book to know you got the answer right, right? But you also can't just use your calculator to give it because I'm going to expect to see the work that showed where all those pieces of information came from. All right, we have one more question that we're going to look at, and it's one of those sketch ones. We're going to sketch a graph with a lot of properties. I chose the most complicated one in your book to do to class, okay? All the ones you have are no harder than this one. I chose the hardest one. This has a lot of information. It tells me that f of 0 is 0, f of 3 is -1. So those are both actual points on the graph. And then it tells me some information about derivatives both before and after the 3 and the 0 and between them. So as I'm taking a look at the graph, I think it probably just makes the most sense to start plotting what they're giving me information about. For instance, I know that I have the origin as one of my points, because that's what f of 0, 0 means, is that I've got the x value 0, y value 0, so I've got the point right here at the origin. All right, so that's taking care of this piece of information. We've drawn that in. The next piece says that f of 3 is -1. So I've actually got this piece that I get to put in there automatically as well. Now it's telling us some information about what happens before and after 0 and 3. And then also in between as we keep moving through. So this first piece tells us that after an x value of 3, what's my slope doing? The slope is less than 0, which means the graph is decreasing. So from this point, I'm actually supposed to be decreasing down. So you can draw it decreasing down in any whatever fashion you'd like, but it needs to be going downwards. So I'm going to draw mine like this. You can draw yours whatever you want. It's decreasing after x equals 3. So we did this piece. Now the next one tells us before x equals 0, what's the graph doing? The graph is increasing because the slope's positive. So I'm supposed to be increasing until I get to that point at the origin in some fashion. So that's not drawn right, sorry. Let's go with this, just plain old straight line. Now it's the parts that are in between that are a little bit more complicated. They reference the x value of 1, so they're telling me that between 0 and 1, and then between 1 and 3, it's also got a slope that's positive, right? So I also need to be increasing between 0 and 1 and 1 and 3. So this whole portion of the graph, I'll mark it in here right now, I need to be going uphill. Okay? But it may not be smooth, or it may not have sort of a nice picture to it. And that's what the rest of the information is that's telling us. They're telling us right here that the slope at the x value of 0, that is the slope right here, is supposed to be 0. What does that look like? Flat. I need to have a tangent line that's flat. So somehow it has to flatten out at that point, which means that probably this was not a good way to draw it. So I'm going to go back and I'm going to alter what I did. I'm going to draw it more like that x cubed graph that I've been drawing before. I'm going to flatten it out. Okay? So that actually takes care of, I did this one, and I did this one now. It also tells us that at x equal to 1, or f prime of 1, it doesn't exist. So what could happen at 1 that would make something not exist? You got lots of choices. Asymptote, what else? It could have a cusp. That's one of those sharp turns we've talked about. What else could it have? It could have a hole. So you get to pick. You guys said asymptote first, so I'm going to draw an asymptote. Okay, but you get to pick however you want it to be. Something happens at x equal to 1, and the slope doesn't exist. Now, the slopes still have to be positive before, and it has to be positive after 1. So I still have to have increasing graphs in some fashion. So maybe, since I did an asymptote here, I can do this. Maybe. That'd be okay. We could do that. I still need to be increasing between 1 and 3. And I'm also told that at 3, I have a slope of 0. So that's kind of a problem because that doesn't look like a slope of 0. That looks like a cusp, doesn't it? Because it's really sharp. So I probably need to fix what I did over here too. How I started out isn't going to work with the rest of information. So maybe I have something like this. It's a slope of 0 here. It's increasing from 1 to 3, and it's decreasing from 3 on. So the more information you tack on might change the picture that you thought you were creating. But the picture can all come together. Now, there's other ways we could have drawn this. Did we have to draw an asymptote? We didn't. We really did not have to draw an asymptote. We could have drawn other things there. We could have drawn, like you said, a cusp, or we could have drawn a hole in the graph there. So there are variations of what this could look like, but they certainly still all have a lot of the same details. Any questions on this one? All right.